welcome back. Yesterday we talked about momentum and impulse and how momentum was a measure of how hard it was to stop an object. Impulse was equal to the change in momentum, and we learned about fat mob. But the whole thing with this was setting up was the second most important law in all physics, which is the law of conservation of momentum. Now, by definition, we're just going straight up definition. By definition, the system of an object which no outside forces acts. Now, okay, that's what makes this a little bit different than energy. With momentum, no outside force can act on it. So, for example, if I'm just rolling an object along the floor, momentum is not going to be conserved because friction is acting on it. However, if I'm standing here and I push off on something, or if somebody's standing here and we push off against each other, momentum would be conserved there because those forces would be internal. I would be exerting a force on the other object or that other person. And since there would be an internal force to our system, momentum would be conserved. So it has to be an internal force, not an outside force. But we say the momentum is conserved vectorially, which means it's conserved in all directions. Now, we can write this as law of conservation of momentum which I will, from here on out, refer to as loco P, or locop. So we had loco E for the law of conservation of energy, loco P for law of conservation of momentum. Now, what makes this also a little bit different than energy is, as we stated, momentum is a vector. So therefore, momentum is conserved in the x direction, momentum is conserved in the y direction, momentum is conserved in the z direction. We will never have to deal with z. Don't worry about that. Not in here. Okay? But you have to break them apart into those components and only look at that particular direction. So I'm going to write this out as conservation momentum, that if you sum up all of the momentums, initial, they will equal the summation of all the momentums, final. And I'll put this off on the side in x, oops, and let's try to make that a little bit cleaner. In x, y, or z direction. Yep. And we're going to do just like we did before with the law of conservation of energy. We're going to break this apart. So when we talk about the initial momentums, this is our law of conservation of momentum right here. You're always going to start with this situation. Where you then go is you take a look and you look at each individual case. If there are two objects that are acting on each other, then you would have, oh, my initial momentum would be the momentum of my first object, initial, plus the momentum of my second object, initial. And let's say they hit and stick together. Well, then they become one object. So that would equal just P final. Now, if there's two objects, so again, this is one situation. I'll put an asterisk. Another situation would be, let's say there's two objects ahead of time. So P1 initial plus P2 initial. Let's say they hit and bounce off of each other. Then I would have P1 final plus P2 final. Okay? So, and I'll give you one more just for an example. Let's say there's one object that kind of blew apart into three different pieces. So if it started off as one object, then it would be just P initial, and then that would become P1 final plus P2 final plus P3 final. So I can't give you a exact equation for the law of conservation of momentum other than this one right here. Your individual equation you're going to build will stem from the conditions. Are there two objects before and two objects after? Is there 10 objects before and one object after? Every time your equation will differ. From once you get to this part right here where we have this part initially made out, you can then expound on it and say, all right, well, P1 initial, that would be the same thing as M1 V1 initial plus M2 V2 initial. And that's going to equal, since it becomes one object, the sum of the masses. Oops, erase that 1 second. The sum of the masses, so M1 plus M2, because they became one object, times V final. If I were to expand on this one, it would be M1 V1 initial plus M2 V2 initial, and that's going to equal M1 V1 final plus M2 V2 final. Okay, and I'm not going to write out the third one because you kind of get the idea. Okay, but this equation, which I'll circle here in blue, these equations you can't build until you know the situation. That's why I always tell you, start with this one right here. Always start with law of conservation momentum. Total momentum before equals total momentum after. And then from there, design the equation that you need. Now, momentum is conserved in all cases when the external force is zero. We've talked about that. So when objects collide, the total momentum of the system is constant, even though the individual momentums may change. We saw this in our thing. Okay, the total momentum before and after, if you add them all up, has to be the same, but the individual momentums, individual velocities of those objects will change as well. Okay? And if objects push away from each other, so if two objects are initially stationary and you push them away, they will have the same momentum. Because in that situation, and this is a special case, I'll put this here, special case, okay, initial momentum is equal to zero. Therefore, final momentum must also equal zero. And a great example of that is if you have ever shot a shotgun or a rifle or a handgun or even watched YouTube's videos on it, where they have the epic fails. Okay, initially, if you're pointing it up, you're holding the gun and the bullet have zero velocity, therefore zero momentum. As soon as you pull that trigger, then the shotgun slug or whatever goes forward, and the gun itself comes back. So one has a forward velocity, the other one has a backward velocity. So best example of that would be shooting a gun. Shooting a gun. Okay. So, or a cannon or anything like that, or something along those lines. Okay. Now we're going to look at two different types of. We're going to look at a lot of collisions with law of conservation of momentum, and we're going to look at two in particular. The first is called perfectly inelastic collision. In a perfectly inelastic collision, the two objects collide and then remain stuck together. And so you have one object here, and I'll just put it here. Here's one, and it's going to have a certain velocity. And let's say we have another one. I'll put that in orange. And it has another velocity. So this is our before. Afterwards, they will have one, they're going to come together. So there's our orange and our red all stuck together. So I'll put this in as green as 1 plus 2. 1 plus 2. And it's going to have a certain velocity in whatever direction we can. Or whatever. So this is a perfectly inelastic. Now, one thing I want to point out here. Momentum is conserved. Oh, I should put in the after. Okay? Momentum is conserved, but energy is not. Kinetic energy is not. Okay, very, very important thing. The difference between that and the elastic collision is in the elastic collision that the momentum and the kinetic energy are conserved. So you could have two objects before, and it might be more than that. It could be more than that too. Two objects before, and then they bounce off. There's two objects after. And this is just an example. Now, okay, in this situation, both E and KE are conserved. Now, I do have to speak about this really, really quick because this is our last one, basically. Okay, most of our collisions are neither perfectly inelastic or elastic. Okay, most of our collisions are somewhere between. They're called what's called just an inelastic collision, where they're going to hit and bounce off. Momentum is still conserved, but energy is not. Elastic collisions really only occur on the subatomic level. Okay, and so these are very, very rare. We won't deal with these much. Okay, they don't generally happen in our macro world. Okay, but very important to remember that when you're doing these, Momentum is a vector quantity. So direction is extremely important, right? So direction, oopsies, direction is very important. Kind of growled more than I wanted there. So if you have an object that's coming in going to the right and it hits and it bounces off going to the left, those are two different directions. One of them has to be negative. It doesn't matter which one, you just have to decide that right from the get-go. Got it? So direction is extremely important because of the vector nature. Because of vector nature. And we're going to do a lot of sample problems with this tomorrow. So that's it, okay? This is the end of chapter 6, okay? There's a lot, there's an awful lot of problems we're going to do, so we're going to do a lot of practice with this, because again, it is the second most important law in all of physics, okay? But you kind of have the general gist of it all now. So that'll be it. I'll see you all tomorrow. Everybody have a great night. See you later. Bye.